Right, so then today's lecture will be about advanced applications in computer vision and robotics. Let's start with computer vision, trying to make a computer see. The first thing we'll look at in computer vision is object detection. The task there is that you give an image to a computer, and the task for the computer is to understand what object or what objects, plural, are in the image and where they are in the image. This is a hard task. And what I'm going to do is give you a sketch of one of the leading approaches right now in computer vision to give you an idea of what the typical ingredients are to build such a system. And you'll see that you understand a lot of these components. So one of the winning approaches right now in object detection is essentially HOG plus SVM. What does that mean? HOG is this thing that looks at an image and shown over here. So your HOG will look at an image, will run a edge extractor on your image. What does that mean to run an edge extractor? That means that you take in the image, and if you look at a pixel and you essentially take the derivative at that pixel, both to the left and to the right, top and bottom, what you do is you say, oh, is the pixel to the left? Take the difference between the pixel to the left of you and the right of you. If that's a high difference, that means there's a lot of high frequencies there. There is some kind of edge information happening. You get a high response. And if there's no edge there, then neighboring pixels will have very similar values, and you get a very low response. So low response is shown in black here, and a high response is shown in white. And so by just running a difference filter, left to right and top to bottom, and then you can, that way you can compute the horizontal gradient and the vertical component of the gradient in your image, you get essentially something that looks like this. Then what you do is you look at this edge filtered image, which is believed to capture more of the essence of what's in the image than the original image, meaning that we're trying to go from an image to something more abstract that will generalize better than the original image. And just looking at edges, you might be able to generalize better because now you're not paying attention to, let's say, patterns on the let's say the fact that this is a green patch doesn't matter. What matters is the outline of the person. Once you have this edge image, you then say, well, if I want to generalize, well, I don't want to just feed this edge image into my classifier and just use this edge image as the pixels in the edge image as features, because I know that if everything had shifted just a little bit, then it would still essentially be the same thing that's in the image. So you want to build in some invariance to slide shifts and maybe slide rotations. And the way that's done is you then start looking at windows in your image. Let's say a window like that. In that window, you look at smaller regions. And in these smaller regions, you look at the edge pattern. And you build a histogram of the edge pattern in these smaller images. So what you see here is histograms of how edges are directed in smaller images inside that region. So, for example, over here, it's saying that in all small regions in that region, edges tend to be diagonally climbing up to the right. That's what this is representing. And by doing this, what you get is you build something that's invariant to shifts by building these histograms here in a way that is discretized. So you build your histogram, you don't say, oh, exactly 55 degrees, exactly 56 degrees, and so forth. You actually bin it maybe in 16 bins, so only 16 orientations really exist. You then have a histogram of how much each of these 16 orientations is present in that part of your image. And that is believed and empirically found to give you a better representation of your image than the original one, in that when you look at something like this, it'll be easier to learn a classifier that then applies well to new images. So let's take this to the test and see how well this works for you. Here is an image to which we applied the HOG extractor. So an edge filter was applied, and then for each region, we histogrammed how much each edge direction in just 16 directions was present. Now the question is, can you see what is in this image? Who has an idea of what might have been in the original image? Okay, what do you think? Bicycle. Who else thinks it was a bicycle? All right, so this is great. Even though the original image has been obfuscated in some sense quite a bit, the essence of a bicycle is still there. You don't know which bicycle is in the image, but it could represent a wide range of bicycles this way with one image here. If we look at the original image here on the left, there's the original, that's the bicycle. On the right is what you get after you apply a hog to that image. Originally, this came about when people were working on building detectors for pedestrians. You can imagine if you want to build an autonomously driving car, something really important is to reliably detect where pedestrians are, because those are your most dangerous things to run into. Well, not for your car so much, but you still don't want to hit them. And so people started analyzing images and tried to build classifiers to see if they can detect pedestrians reliably. And what came out is that, well, this hog thing was a good way to represent your images, to capture the essence of a pedestrian. Then other people started saying, hey, how about we apply this hog as a way to represent any image? And they found that for many, many types of objects, this hog representation is a really good way to go. So let's look at the entire pipeline, right? Back here, let's see. It says hog plus SVM. So this is the first phase. After you've done this, you'll have many of those because you'll have many, many images, right? And they'll be labeled, let's say, person versus cat versus dog and so forth. And you'll feed these into an SVM, which will then learn how to map from a hog image, which looks like this, onto a class. So how does that work in practice? There's actually some subtlety there that's pretty important. The first round is what we are used to. You found your feature space, which is this hog images. You find positive examples, let's say, for people or for bicycles, whatever it is that you're trying to detect. You have those labeled. Then to find negatives, you just take whatever images you find that were not labeled as bicycle. Some of them will actually be bicycles, but that's fine because we know our classifier algorithms like SVMs are robust to a little bit of noise. And we know that most of the randomly downloaded images will not have bicycles in them, so it'll be a limited amount of noise. You learn an SVM, you do some cross-validation and so forth, and you hold out data, get your hyperparameters right. There's your SVM. Then the next thing you do is something called bootstrapping, or mining hard negatives. And what you do is you take your classifier, you start downloading more and more images, and on each of these images, you run your classifier, and you see what the score is. Let's say positive is the bicycle class, and negative is not bicycle. And you take anything that has a score higher than -1. Remember that negative should have a score lower than -1, positive should have a score higher than +1 in a support vector machine. So anything that's kind of close to the boundary here of the negatives, you take in, and those are going to become your new training examples for the negative class. The result of that is that you really zone in on the decision boundary and on the hard ones. Instead of just randomly having examples that you put in your negative class, you now have the really hard ones in your negative class, and you can refine your classifier and get a better one than you had in the original training round. That gives you your final SVM. And in practice, the way it typically works for these detectors is when you get an image, you'll actually apply this classifier and this hog extractor at different scales to a given image. Because it's not necessarily the case that whatever you're trying to classify has to be centered in your image. It could be anywhere in your image. So you will, from your original image, generate many, many images by traveling over the image, windows of different sizes, different positions. Run the classifier many times. And if for any of those windows your classifier fires as, yes, there's a bicycle here, then you say, okay, I now know where in this original image there is a bicycle. You will do this for every class that you care about. So if you have, let's say, 20 categories, then you'll run 20 of those. And you'll only detect things for whichever one fires the highest. So let's take a look at how well this works. Here is this approach applied to detecting sofas. And this is test example, so this is pretty good. This is pretty good. It's only part of the sofa, but it's not too bad. This one here, that's not a sofa. That is a windowsill or a table with cats on top of it. That's state-of-the-art computer vision. Just to let you know that there is still a lot of research to be done there. That's a sofa that's reasonable. Bottle. Okay, finds a ketchup bottle here. It then finds some kind of bottle here. It finds the two bottles here. Finds something it thinks looks like a bottle, but it's definitely not a bottle over there. And then it finds a cone over there, and it thinks it's a bottle. Okay, again, lots of room for improvement. Then cats. People love cats, and it seems like they built really good classifiers for them. Cat, 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 cat. That's all good. Person. That's what's originally what the hog feature was developed for, pedestrians. So this is pretty good. There's a person there. There's also people here, but that's very few pixels to realize it's a person. So maybe it's okay. It doesn't find them. Here, finds this one, not this one, not this one, not this one. Here, that worked well. That worked pretty well here. And that worked pretty well here. That's a person on a motorcycle. So there's a lot of occlusions, which makes it hard. You only see part of the person. Still gets it. Car. That's good. That's pretty good here. That's good. That's good. And that's good. So that worked pretty well. Horse. That's indeed a horse. That's a horse with a lot of occlusions. That's pretty good. Another horse. This is a cow, but thinks it's a horse. This is the wheels of an airplane. It thinks it's a horse. So what's going on here? What's going on is that this hog representation doesn't really capture everything. Could be one explanation, right? And that it just, once you look at the hog image, a horse and the wheels of an airplane just look the same. If you're computer vision research, you could go in, look at the hog images of these examples here. You could say like, well, looking at this hog representation, can I really tell the difference? And if the answer is no, I can't tell the difference, that means you made your features a little too general. They can't be specific enough anymore. You need to think of adding in more features that can distinguish these things. If you look at your hog image and it just looks nothing like a horse, it looks like the wheels of an airplane in your hog image, then what that means is you probably didn't have enough training data yet. Or maybe your linear classifier isn't powerful enough. Maybe you need to switch to a different type of classifier. It could still be an SVM, but now maybe using a Gaussian kernel or some other type of kernel to have a more accurate decision boundary. Okay, that's one way to go. Here's another way to go, which has become popular over the last few years, and they're kind of going head to head right now in computer vision. And this approach is called deep learning. And the idea here is that, well, standard computer vision, if you look at what people do, they use these machine learning tools, support vector machines, maybe some special kernels and so forth, together with a lot of insight about how images are being formed, and knowing that, for example, for changing lighting conditions, edges will stay roughly in the same place, but a lot else about the image could change, and that's why you go to an edge image rather than the original image. So a lot of insight about image formation goes into designing these features. And a lot of the progress in object recognition in images comes from very clever ideas about what features to use. I represent this hog to you in a kind of simplified way in the sense that I said, look, here it is, but until people found that one, people were trying many, many other things, and it's only when you find the right one and it works really well. In hindsight, yes, it's clear that was a clever thing to do, but it took a long time before people actually had this exactly right. Now, you could say, well, it's all great, machine learning does the final fine-tuning of some weights. Can it do a little more for us? Can it maybe find the features for us? If it could, then we don't have to think ourselves about image formation. We just kind of feed a lot of images into it. It'll make the features for us, and then it'll learn the classifier at the end, and there we go. It's kind of what people used to do in the very beginning. Early days of AI, they would be very optimistic and hope that you can feed something in like a raw image, and somehow the machine would learn what's in the image from a few examples. And people kind of got stuck. But recently, there's been some progress in how to potentially make this work. There was a big article about this in the New York Times in the summer. The title of the article was, "How many computers to identify a cat?" The answer is 16,000 cores, at least according to this article. What this is referring to is a project called the Google Brain Project. This is a project that's part of Google X, and the people leading this particular project were Andrew Ng, Jeff Dean, and Kwok Lei. And really what they were working on is having machine learning learn the features, and then they showed in this particular result that with 16,000 cores and quite a bit of time of running these cores and processing data, you would actually learn features that correspond to meaningful things, like cats. Like, it would have a feature learned, we say, what does this feature mean? You visualize the feature, and you get cat faces. That's pretty cool, right? So they actually learned something there. They didn't put in anything about edge detection and so forth. It just learned the concept of a cat face. So let's take a look at how this works. Here's the basic building block that we already covered. It's called the Perceptron. It was brain inspired. The idea was that you have some features coming in. They get weighted, they get summed, and then you check whether the signal is bigger than 0 or smaller than 0, and that allows you to classify. Okay, that's going to be our basic building block. We're going to have many, many of those in our architecture. So here's the first extension of this. This is called a two-layer neural network. This part here, let's see, this part here is still the same as before. That's a perceptron. You have features coming in. You have them being weighted, summed together, and then instead of checking whether it's above 0 or below 0, often things get squashed then. So instead of keeping your original signal, that could be from minus infinity to plus infinity, you feed it through this squashing function that puts it between 0 and 1. And then you might decide if it's above 0.5, it's one outcome, below 0.5, it's the other outcome, which is the same thing as originally being below or above 0. So far, not a big change, except for this squashing function here. Now what we're doing is saying, well, we don't really know what features we should feed in here. So why don't we do something very similar in the previous step? So we say, to decide what this feature is going to be, we're going to use a perceptron with this squashing function that puts the value between 0 and 1. And then we feed the original features into this perceptron here. What we do now have, we have something that, in some sense, runs a classifier over the 3 original features. The result of the classifier is then fed in as the first feature to this final perceptron. We have a second classifier sitting over here. It feeds its result into the final classifier. And we have a third classifier over here feeding its result in here. So rather than using the original features, we learn 3 classifiers from the original features. And then the results of these 3 classifiers are then fed into the final classifier. You can imagine this could do something more interesting. You can imagine this could do something like first classifier detects a front wheel, second classifier detects a back wheel, third classifier detects something like a seat, and then if all of these come out positive, then you feed on, and the last classifier says, yes, every part was present for my bicycle. Something like that. So that's the idea, that rather than using the original representation, we're going to cascade these classifiers. And what's nice now is that we are more expressive in that we not just have these 3 weights here, we have another 9 weights over here that can be learned, and that gives us a lot more expressiveness in terms of how we go from the input image to the final result. Okay, you can actually repeat this process. You don't have to stop with just one additional layer. You can put as many additional layers as you like. And then here will still be a classifier at the end which says bicycle or not, for example. But what's happening here is a cascading of classifiers. And what you can imagine is happening is that what's coming in here is something like raw pixels. And maybe these first classifiers detect things like a vertical edge, a horizontal edge, a diagonal edge in the other direction. Then the next layer of classifiers could maybe detect something like the combination of a vertical and a horizontal edge. And that way you can start building things up that are more complex. And the further you go along in this direction, the more complex an object your classifier is able to classify. Because you've had the ability to turn your pixels into something a little more abstract as you go from left to right. This was done, this type of architecture was already presented back in the 60s. People started doing AI. They said, let's build a neural net. It was actually shown that with this type of architecture, if you had some input here, and some output here, right? You can think of this as just a function. You go from input to output. It was shown that even with just 2 layers in the middle, if you have enough of these perceptrons stacked above each other, but just 2 layers from left to right, you can approximate any function, any smooth function, arbitrarily well. Meaning that no matter what your actual function is that you're trying to learn, with just even this part of this, and if the inputs went into there, just that stretch you could approximate any function. Now, of course, the fact that you can approximate any function means that you can easily overfit, because you can approximate any function, so many possibilities of things that you could present as your hypothesis for classification. So there's a little tricky part there. You need enough training data to make that meaningful, right? But the upside here is that you're not going to be limited in terms of expressiveness. You're going to be able to capture whatever it is that you might want to capture, but maybe you just don't have enough training data to zone in on the right thing. Aside from not having enough training data to zone in on the right thing, another thing that could happen is that, well, there's a lot of weights to be learned here. Every edge is a weight. That's a lot of numbers. You could say, well, I'm going to find the numbers that make the classification as accurate as possible. Well, we know how to do that. It's called, let's say, hill climbing. You have some weights, you perturb them, you see just a little bit, you see if the perturbed weights do better on your training data. If they do, you keep the perturbation of your weights, and then you repeat. And that way you hill climb towards a better set of weights. But we know that with hill climbing, the problem is that you'll easily get stuck on local maxima, right? So that's a problem. Here is just a 3-dimensional space, really a 2D problem, embedded in a 3-dimensional space. For these neural nets, if you want to do something really expressive, you'll have maybe millions, if not billions, of weights. So you can imagine if you're working in a 1 billion dimensional space, there's a lot of local optima that you could get stuck in. A lot of the ones that you don't want to find. So you have 2 big challenges here. One is, how do you get to the right local optimum? Another one is that you might need a lot of training data. And I would say in the last kind of 10 years, people found a way to resolve both this problem here of potentially getting stuck in a bad local optimum. They found a way around that, and they found a way around the fact that you need a lot of training data. Here's the idea. The idea is to not directly start building a classifier, but first build something called an auto-encoder. What's an auto-encoder? It looks a lot like what we were just looking at. This is again the perceptron structure. Perceptron structure. Same here, same here, same here. But what we're doing now is we're feeding in the features, F1, F2, F3. And rather than trying to make a classification at the end, we want it to spit back out the features at the end. And now we can do a hill climbing procedure on the weights that are sitting here and here, where the objective is now to reproduce the input as faithfully as possible on the output side. You could say that's kind of lame. I mean, already had the input. Why would I want to reproduce it at the output? The idea here is that what these layers are supposed to represent is something more abstract about your input, something that generalizes better. So you will actually not request to reconstruct your input perfectly. You're happy with a little bit of reconstruction error. And what you'll really be going for is a representation here that has interesting properties. So one way to think of it is that you want to compress it. You want to have less bits in the middle layer. And so you somehow compress your input to less bits. Since you have less bits in the middle layer, that means you somehow need to capture the essence to then be able to reproduce the original input as accurately as possible. So one way to think of it is this side is compression, and this side then is the decompression back to the original. What that means is that your objective function here will be an additional term here. You minimize the reconstruction error, but then will also be something here where you minimize, let's say, a number of bits used in middle layer. In practice, what this actually tends to be is something where you say, In the middle layer, each unit has an activity between 0 and 1, because we squash everything between 0 and 1. And you'll try to minimize the activity in the middle layer. Keep it as low as possible, while still be able to reproduce the inputs fairly well on the output side. So you try to keep the signal here as low as possible, which means if there's anything that's not really that relevant about your input, you'll just lose it and you won't represent it on the output. Now, the important thing here is that you don't just do this on one input. You'll have many, many images. And for all these images, you will have to use the same auto-encoder, right? You can't tailor your compression scheme to the particular image that you get. You have to have one computational scheme here that will take in any image, compress it, and then bring back out something close to the original image. So this is a separate training procedure. It's not a classification training procedure. It's a bit like clustering in many ways because you're trying to find structure in your data, but in a very particular way. Now what's nice about this is that you have a lot more supervision. Originally, all we had, let's say if you had a 16 by 16 image or maybe a 256 by 256 image, you'd have one bit. It says there's a bicycle here or there's no bicycle here. And that's all that you had to supervise this whole process. What you get here is every original pixel, so to say, is training signal and is something you try to reconstruct. So you have a lot more supervision in this process than you would in a standard classification task. Every pixel is providing supervision, as opposed to just your classification label. So this way we get around the issue of needing lots of training data to learn these big things. And the main idea is that by learning these compressed representations, maybe we're learning the right thing. So what you would do is you say, learn an autoencoder. This first layer is a compressed version of the input. Then you say, now I know how to compress inputs. Let me take all my input images, compress them, and then repeat this procedure. The compressed version of the image is now going into my autoencoder, which learns to compress the compressed image and find something yet more abstract in its middle layer. And you keep repeating this. And that way you get a stacked version of compressions. And at the end, you presumably end up with something that is a fairly abstract representation of your original input image that is a better feature than using raw pixels, or a better set of features than the raw pixels. Okay, there are a couple of details that you need to pay attention to in that you can't just compress the way I described with just perceptrons. You also have to build in something that says, oh, if I'm off by 1 pixel, that doesn't matter. And you need to do some kind of feeding the output of multiple perceptrons into something that just takes the max of them. That way, for a certain region, you take the max of several perceptrons acting in that region as your output, just to make it shift invariant. But the key idea is really the stacked autoencoder. So this is what it would look like. You would have a trained neural network where you never saw any labels. You don't even know what you're going to try to find. Are you going to find bicycles, airplanes, pedestrians? You have no idea. All you know that you are going to work with images, and that by training this autoencoder one step at a time, this is the one you trained first. Then based on that compression, you train the second one, which is sitting over here, and so forth. Last one sitting over here. And these outputs here are presumably more abstract representations of your input that are meaningful for many image processing tasks. So what you do then is you could look at these, and this is what they did in the Google X project, Google Brain. They said, let's look at one of these output neurons here. They didn't even know they were going to look for cats. They just looked at one of them, and that was activated a lot. Then it said, let's now go through all our original images and rank them by how much they activate this particular neuron. And if you rank original images by how much they activate this particular neuron, these are the top images that come out. So what you see here is that this sequence of compressions somehow learned an abstract representation that captures the idea of a cat face. And if you were now wanting to learn a classifier for a cat face, you have a really good feature here. Right? That's a really good feature, because that thing will be really high whenever it's a cat face. You don't have to learn anything particularly complex. You do something almost as simple as, whenever this is high, yes, it's a cat phase, and when it's not high, then maybe it's not a cat phase. So this is really interesting, and part of why these results are coming around now is because it takes a lot of computational power. So that took 16,000 cores. People have found ways to run it on less machines since then. It also took, I think, 1 billion images they took from YouTube. So they took 1 billion images from YouTube. And so really what this is saying is that if you want to compress images that you randomly grab from YouTube, a compressor that will naturally come up is a compressor that in some sense identifies cat faces. It can then just say, hey, this image has a cat over here. You just need to reproduce a cat face, and that's all you need to do to reconstruct the original image. And that's a very effective way of compressing these YouTube images. So if you had taken a different data source that didn't have as many cat faces in it, you would have probably learned different things over here than they did. But that's fine, right? Ideally, you get all the data that you can possibly manage to process, and you will learn, there's also ones that correspond to faces. So the main ones they found were ones corresponding to faces, and the secondary ones were the ones corresponding to cat faces. And just the thinking is that if you could do this with more data, not just 1 billion images, but even more, then maybe you could also find other things. Maybe next you find dog faces, or yet something else. And the more data you have, the more interesting things you can find in this last layer here. All right, then you put your classifier there, and now you have potentially, you still have to do training here. You'll still run a perceptron or a support vector machine. All your images will now be represented with their output over here. That will go into your classifier, labeled for whatever task you're trying to solve, and there's your classifier. All right, any questions about that? Yes? So typically what you have to do in practice is once you have trained it up to this phase over here, let's see. Once you've done all the training, you have your stacked auto-encoders. You will have features that are fairly informative about certain things. If you had enough data and you did this exactly right, you'll have informative features. And what people try to show in the results people are after is things like, if I only look at this last layer and represent my image by what it would output coming out of this pipeline here, what would come out of this last layer here, and that's my new representation of my image. If I feed that into a supervised learning algorithm, let's say a support vector machine, see how well I can do. And if you can do really well based on this output over here, then somehow whatever pipeline you build here was abstracting your image in a meaningful way. And people have indeed shown that you can just look at the end layer and get really good results on many image processing tasks. In practice, the tasks they've looked at aren't entirely the same tasks that people have looked at with the HOG plus SVM, so it's not clear right now maybe which is the winner between the two. And of course, people are building on top of both of them and pushing things forward. But it is true that they have found very good results just looking at that last layer output, saying that's my representation. But it will still train an SVM. It will train often still an SVM with a fairly complicated kernel, maybe a Gaussian kernel, which means you end up with a lot of training data that you need to store at the end of the day to be able to run your classifier. Any other questions about this? Yes? Okay, so here's something interesting. So here's a little more detail on this. When you train these, you train them like this. You train one vertical layer at a time. The input will be, for the first layer, will be the original image pixels. But then once you've learned one layer, the output of that first layer will be the input for the second layer, right, and so forth. So you learn this all at once. And I think the best way to think of it in this context of the context of this class is just doing some kind of hill climbing procedure. In practice, it's often running some variance. It could be a first order method, some stochastic gradient descent. It could be a second order method that might sometimes converge faster, but in terms of iterations, but every iteration in and of itself takes more time. So people are playing with these algorithms and trying to find out what is the fastest. because they are bottlenecked to some extent by how fast they can train these over large amounts of data. So it's still work in progress to determine how really you want to train this. But the general idea is that you have an objective, you try to get the weights such that the objective is as good as possible. Now, once you're done training here, and you bring them all together, often there is some kind of fine-tuning training where when you build this classifier, rather than just building the classifier right here, at this point you actually build think of this entire thing as your classifier. And you do a hill climbing on all weights at the same time. And you could say, well, isn't that what we originally had, where we had all these weights and we need a lot of training data and we would get stuck in bad local optima? And the answer is yes, this is the same, but the difference is that you are initialized in what seems to be a really good spot. And so the local optimum you find, and for sure it's going to be a local optimum, not necessarily the global one, is actually a good local optimum in many of the experiments people have run. And so it tends to work out that way. It's a way to kind of position you in the right spot of the space, and then you can fine-tune your classifier from there. So it does happen that the entire thing gets updated. That tends to give you the best performance overall. Any other questions? Okay, let's switch gears then in terms of computer vision and look at something completely different. So we looked so far at object recognition. Now let's look at computer vision as the inverse of computer graphics. If you do computer graphics, you have a model of the world, and from that you generate an image. So you could imagine that computer vision would think of that image as a sensory measurement, and you use Bayes-net inference to back out the model of the world, the lighting, and so forth. So that's this Bayes-net over here. So what's in there? We have a depth image over here. So this is from the camera viewpoint because you're going to generate an image with one camera here. So how deep is everything in every direction? You have light. You say where the light is coming from. When you combine those, you can in principle render your shape. But you wouldn't know yet what kind of paint is on your shape. So paint or reflectance is another variable here. Once you combine that with the rendered shape, you get the actual image, which could look maybe something like this. And so what we're after now is, given the image, can we back out what's the paint, what's the depth, and what's the light? So here's our Bayes-net again. We want to recover from just the image paint, depth, and light. So that's just a standard probabilistic inference query, finding Z and R, the most likely ones, given the image. Now, to do this, there are a couple of challenges. One of them is, well, we need to know what these probabilistic models are. What is PZ? What is PL? What is PR? And then, of course, we also need to know these. Now, these two in the back here, those we know from the theory of how image formation works. So we can build those up from first principles. Now, these ones here, we cannot build up from first principles. What's the distribution over depth when you know nothing else? Well, you need to collect a lot of data and somehow build a model over what is the prior for depth. Same for light. You need to build some model for what lighting conditions typically are like. And same for paint. You need to build some a priori model of what painting typically looks like. So these you have to learn. And a lot of the work that resulted in the results I'm going to show you goes into finding good distributions here from data, maybe a combination of data and first principles. Another challenge then is, how do you do inference in this? You're trying to recover a lot of variables here, given a lot of other variables. It's a complicated inference problem. Let's take a look at the resulting procedure in action. So I haven't told you how the inference is happening, how those models are learned, but you get the picture of that. There is a Bayes-net there in which you could run inference. So what are we looking at here? Let's reset this. We have the original image up here. This is the depth image we're trying to recover. This is the paint we're trying to recover. And this is the rendered This is the light we're trying to recover, and this is what the shape would look like with this light. And as the procedure goes on, we see that indeed we get a pretty meaningful recovery of what depth, light, and paint look like for that original image. The reason you saw things evolving, because something like a hill climbing procedure is being run. Some effective hill climbing is done that will take you from some initialization to a pretty good local optimum in terms of probability of these generating the image we saw. Here are some other examples. So the left is the original image. The second column is the depth image that was recovered. The third column is the paint that's recovered. The fourth column is the lighting condition, as well as the rendering of the shape with that lighting condition. You can see sometimes some of the paint bleeds into the fourth column, meaning that it didn't perfectly get it, but these results are very impressive in that it really gets the overall gist of how this image was formed. It's actually, by the way, this is some work done at Berkeley here. Here's some more example results. You see this actually works quite well. Here is something you can do. Once you have the system in place, you can now start using it. You can take an image of something. You can back out shape, paint, lighting. Then you can start playing yourself with the lighting conditions, the paint, and the shape. And you can start making movies where you have a variant of your original object showing up in these movies. So you can do some pretty realistically rendered scenes this way. In this case, again, a cat. All right, let's take a break here. After the break, let's look at some robotics applications. Robotics. Today we'll look at robot helicopters. Next time we'll look at some subjective view of mine on where I think some of robotics could be headed and some of the things we're very specifically doing at Berkeley. But for now, let's look just at some cool robotic stuff. Helicopters. Let's say you want to fly a helicopter autonomously. And you say, well, let's do something like this. That's called a tick-tock. It's a maneuver you do if you're a really good pilot and you want to show that to somebody. Which is not a very energy efficient way of staying up in the air. But the question that we're asking here really is, how do you build a controller for this? This is really just like a search problem or an MVP. You somehow want to find the right controls to send to your helicopter such that this thing succeeds. All right, so where do you start? You start with getting yourself a helicopter, remote control. What do you need to do if you want to fly autonomously? You need to know where the helicopter is as you are flying. So you want to somehow track position and orientation. Then you want to decide on the control inputs to send to the helicopter. So two challenges here. One is the kind of particle filtering type challenge. Know what your state is. The other one is make the right decisions. Okay, so how does that work? You have your autonomous helicopter set up, which has a remote going to the helicopter. Then there's a computer that you'll use to do all your computation. You'll go into the back of the remote control, and that way you can send signals to the remote control, which will send them to the helicopter. The channel you use is actually one that originally wasn't made for autonomous flying, but was made for learning to fly. You could hook two remote controls to each other. If you were the novice pilot, you could hook yours into an expert pilot's, and you would be like the computer, you'd be in the back of the other ones, and the other guy, who's the expert, they could overrule your commands whenever they want to. All right, so that's the standard setup, but we just abuse that to put a computer in there rather than a novice pilot. Then on board you have inertial sensors, so accelerometers, gyros, and magnetometers. That data gets sent down. Then to know where the position is of your helicopter, you can put a GPS on there, but the problem with GPS is that it works with an antenna that has to look at the satellites. If the antenna is not seeing the satellites, then it's not going to know where it is. even when it sees the satellites, it takes a few seconds at least to lock onto the signal. So if you do these aggressive things where you're not always having the helicopter straight up and the antenna facing the satellites, you essentially never get a GPS lock. So instead of relying on a GPS, for these aerobatic maneuvers, you want to rely on something else for position. Cameras looking up is one way to go. Okay, then to track the helicopter, that's an HMM problem. At every time, there is a state, which is the position, orientation, angular rate, and velocity of your helicopter. There are some measurements from the vision, from the magnetometer, from the gyro, from the accelerometer. Just to give you a little more detail about this, the magnetometer is a 3-axis measurement that tells you in the frame of the magnetometer which direction is the Earth magnetic field pointing. The gyro in the frame of the gyros will say along each of my 3 axes how fast am I rotating. And then the accelerometer will say along each of my 3 axes how different am I accelerating from free falling. So if you free fall, you measure nothing on an accelerometer. But if you're not free falling, you measure whatever acceleration you're experiencing that's different from free falling. So that's why, for example, if you hold up something with an accelerometer, it's not free falling. It's not free falling by the amount of acceleration you're giving it against gravity. And so you're essentially measuring gravity, which direction gravity is pointing when you hold your accelerometer. For a flying thing, you could be free falling. It's more general. It's whatever is different from free falling is what you measure. Okay, then as time goes by, helicopter dynamics tells you from time t, action at time t, what will be the state at time t plus 1. There's going to be a lot of noise on this. So this is the common representation to using control theory, is to not write it as a probability distribution explicitly, but to say it's a model, f, that tells me where I'm going to land, plus then some random variable that tells me how much I'm not landing where I was supposed to land. And that random variable will have some distribution, maybe a Gaussian distribution with a lot of variance. Okay, so that's how we track. So we just run a forward algorithm in an HMM. Now, because these variables are continuous, you actually manipulate Gaussian distributions rather than discrete distributions. But effectively, the math is the same. The math we saw for the forward algorithm, you just replace every sign that looked like this. You replace that by a sign that looks like this, and nothing changes. All right, so we now know how to track the helicopter. The other thing you need to do is then to control it. You need to have a model for how it behaves and then send out controls. What control inputs do you have to a helicopter? How does that thing fly? It has blades going around. Depending on the angle of the blade, you push more air down or less air down. A very steep angle pushes more air down. And so the steeper the angle, the more air you push down, the more vertical thrust. That is your collective control. One of your control inputs. Then, to make a helicopter fly forward or sideways, you actually can't just directly ask for that. What you have to do is you have to tilt the nose down or roll it sideways to be able to move sideways or forward. And what you use for that is the cyclic pitch controls, these two here. What they do is there's a very clever mechanism built onto the main rotor, and that mechanism allows you to set a difference in angle between angle on the left versus angle on the right, angle on the front versus angle in the back. And that difference in angle will result in a difference in the amount of air being pushed down, front, back, left, right, which in turn allows you to rotate your helicopter, roll, or pitch it. So that's these two controls. Then the fourth control you have is the rudder control. That one is the angle of the tail rotor, which spins so fast you can't see it. You control the angle of the tail rotor. Same thing there. The higher the angle, the more thrust you generate. And what that does is, well, then your tail will rotate around the body of the helicopter. Now, what happens here is that by default, if you didn't have a tail rotor, the helicopter body would be counter-spinning to the blades. Thanks to the tail rotor, you can stay facing in the direction you want to face. And of course, you can also control if you want to move the tail left, right. So those are your 4 control inputs. The effect of these control inputs on the motion of the helicopter is actually pretty complicated. Qualitatively, it's what I described. But if you want to put it down in equations and get it very accurate, it's pretty complicated because the airflow around the helicopter is very difficult to model. So there's a challenge there in getting this dynamics model of the helicopter right. But that's the idea. You somehow model everything that happens thanks to these controls. Based on the past data and controls, predict the next state. And then there's, of course, noise there. At this point, you have your Markov decision process. It's a continuous Markov decision process instead of a discrete one. You can still solve this in a similar way to the way we have solved things. Actually, the way in this case we did it is more similar to search. We'd actually find the sequence of controls that would give the best performance. And then we would execute that sequence of controls. But after executing the first one in the sequence, we would say, oh, with all this noise, not so sure that we should keep executing what we computed in the beginning. So let's recompute, rerun a search to find the best sequence of controls from now onwards. And you keep repeating this search after every step. So it's continuous replanning after every step. In practice, for this helicopter, every 1/20th of a second, it would replan a 2-second look ahead. Okay, so that seems all good. We have presumably a model. We have some way to track the helicopter. We can run this search and replan continuously. The one thing we haven't described yet is what the reward function is. So yes, you can search, but you don't know what will optimize your score. So let's say you were to hover, you could say, well, deviation from the target position, X star, Y star, Z star, needs to be penalized. And then maybe velocities different from 0 need to be penalized. That's what it means to hover. Do this, run this whole mechanism, and after doing this, as a side note, what's interesting about flying upside down, it's more effective because when you push air through your blades, you accelerate that air, and it's going at twice the speed below the blades compared to above the blades. Now that air is passing by the helicopter body and causing friction and dragging the helicopter body down. So it's nice if the body is above so that half the speed air is going over that body rather than when the body is below where you have double the speed of the air before it's dragging over the helicopter. All right, so that's hover. Now, that's all good, but what about the flip we saw in the beginning? This flip was a more complicated trajectory. You couldn't just say, oh, target position, 0 velocity, that's the way to go. So you could say, well, maybe we'll write something else down, right? That's actually what we did. So this is some of my research during my PhD. We said, let's write down what a flip looks like. Flip here. It's some kind of sequence where the position stays roughly in place, and then the orientation just changes in a way that you flip, right? And then we run the same algorithm as for the inverted hover, which seemed quite the way of cracking helicopter flight, so should be a good way to go. And here's our job. We went out for a flight experiment, and this whole tracking system, search for control, not staying in place. That was it for that day, right? We were back a few days later, but this didn't work at all. What didn't work? Well, we were planning these controls, and the computer was crunching numbers and saying, oh, this is the control I need to apply. Came up with these really high numbers. Those high numbers are just not are hitting the limits of what the helicopter can handle. And as a consequence, you make the engine die, and there goes your helicopter. Now, in principle, as a side note, you can save helicopters when the engine is dead. It's something called auto-rotation. But the assumption there is that your blades are still moving around fast. If your blades are still spinning fast, you can go into a mode. As long as you still have your collective and cyclic pitch controls, you can actually angle your blades in a way such that they essentially, one way to think of it is act like a windmill or wind turbine is not exactly that, but you absorb the flow of air through your helicopter blades into blade speed, so you end up powering it by your descent. And then right before you hit the ground, your blades are spinning so fast, you have a lot of energy in the blades. Now you change your angle of your blades, so you generate a lot of lift all of a sudden. That slows you down. And then you touch down. You have one shot at this, because if you kind of generate your lift too soon, you'll be too high up. After you generate your lift, your blades will not be moving anymore pretty much, and you drop like a rock. So you have to time this exactly right. At the right moment, you change the angle of attack, and you can land safely. It's called a successful landing when people in the helicopter still are alive. This is possible with these helicopters too. If you fly in a helicopter, and I thought this was particularly interesting, if you fly in a helicopter and the tail rotor dies, the solution, what will happen is your tail will start spinning around, and you really cannot control a helicopter with the tail spinning around really, really fast. Because the way you move a helicopter somewhere is by reorienting it, and you just don't know which way you're facing. So what you do is you actually kill your engine, because that way you get rid of the counter torque. So now you don't need your tail rotor anymore, which was dead anyway, but now your engine's also dead. You killed it. Now you don't spin anymore. And then you do the same maneuver you would do when your engine died. You go down for an auto-rotation landing, and you hope you time that exactly right so you land safely. Okay, didn't happen here. When the blades are not moving, you cannot spin them up very easily anymore. They start folding up, and you're done. So what about this thing we saw a little while ago, which was apprenticeship learning? The idea there was you play Pac-Man, the computer watches, and then learns from that. So we said, why not do that? This guy, you can look him up. Let's see. This guy here, his name is Alan Szabo. Amazing helicopter pilot. We're watching his videos, and we say, you know, flying a helicopter upside down is really not pushing the envelope of what you can do with a helicopter. What this guy is doing here in a video called Sunday at the Lake is really showing off what you can do. So we need to really go for that. We looked for a pilot that's about equally good as him. Very close. We found a really, really good one. We found the best one in California, pretty much. Said, let's take that pilot out. Let's have that pilot fly the helicopter and see if we can learn from that. So here is what we did. We pilot fly some sequence of maneuvers that are very complicated. 6 times. We track it with our HMM. Then we now replay the position and orientation that came out of the HMM in parallel for all 6 of them. You see that in all 6 cases, he's going through a double loop, then he's doing a stall turn and so forth. It's just not exactly in the same spot every time, because that's very difficult. And if you look at this, we don't really want to fly one of these. What we want to do is we want to fly something that's better than any of these 6. So think of these 6 as, these are some noisy versions of what we really want to do. Let's denoise these 6 and get out what we really want to fly. That would be our target trajectory, and then the reward function would just be penalized for deviating from this target. How do you denoise this? Well, you run an HMM. You don't know what the sequence that you want out. That's the denoise sequence. So that's your hidden state. Your demos are your evidence variables. Now, the tricky part is the timing isn't always the same, so you can't just hook them up at each time. You need to do something extra there. Now, what you do, you say, let's just put something in that hidden state. Then, once we put something in there, we can hook things up in a reasonable way. Use an algorithm called dynamic time warping, which is used in speech recognition and also used in biological sequence alignment. Once you do that hookup, you now have a standard HMM. 2 evidence variables at each time, and then some evidence variables go unused, but that's fine. You run your inference in your HMM, which, when you replace that summation sign by this integral sign, becomes a Kalman filter. After you did that, you hide the connections. You say, let's now rerun how we should hook things up. Rerun that dynamic time warping. Now it's hide the denoise trajectory again. Rerun our forward algorithm. You actually also do a backward pass. That's essentially the same as the forward pass. And there is your denoised version of your demonstrations. So then, now we've done that. Let's take a look at what that is. The white helicopter is the denoised version. The colored helicopters are the original ones, but the side effect of this inference procedure is that they're all aligned in time. So you get to see a nice aligned 6 air shows plus the white denoised version. Now, if you're not very experienced at looking at these helicopters in this graphical simulator, you might argue, I'm not sure this white one is really that much better than any of the others. So here's an illustration that gives you a little more quantitatively how much it is better. So 3 colored ones are demonstrations, and the black dotted one is what the algorithm comes up with as, here's what you should be flying. So capture the idea of a double loop here in a very clean way. Even though some of these demonstrations didn't really look like nice loops. What's going on over here? Probably what's going on is that the HMM that was running the tracking was getting some really noisy evidence at the time, and so it gets out this weird trajectory that's not exactly the right trajectory, and that's what you have to deal with if you work with real sensory data. Your state sequence is not always perfect, so we denoise both for pilot imperfections and for imperfections in us being able to recover the trajectory the pilot flew. Okay, so you do this, you have your trajectory, you now run the same algorithm that you can run for the inverted hover. This, every 1/20th of a second, you recompute a sequence of actions for the next 2 seconds. That means 4 actions per time slice. 2 seconds means 40 time slices, so you have 40 times 4, 160 actions that you're optimizing over. And let's see what happens when you do that in real time. Flips over when it takes off. Turns out when we did this research, there's another research group, Eric Cohen's group at MIT at the time. They were able to do a couple of aerobatic maneuvers. They were the only ones that had ever done aerobatic maneuvers at the time. So they did a split S, they did a snap roll, they did a stall turn. So we figured that's the first 3 things we do. At this point, we can mark the checkbox that we're doing things more than we've done before. These are loops. If your pilot is good, they'll do pirouettes at the top of their loop to show off they're in control. Stall turn is a way of changing direction without burning your velocity into friction. Hurricane is a fast backwards flying circle. The idea here is that even though these helicopters are just about as big as wingspan, it's flying up to 45 miles an hour. And either it's all. These are some of the hardest maneuvers. The reason they're some of the hardest ones is because you keep flying in air that you just pushed around, making it really hard to predict what will happen because that airflow is really hard to model. Here's a TikTok from a while back, beginning of this part of lecture, and the inverted hover. So that all worked out really well. Okay, in the remaining 5 minutes, I want to look at another problem in robotics, which is how to make robots walk, and tie it to some of the concepts we've covered in class. So here's the problem. Here's your 4-legged robot. You want it to traverse rocky terrains like the terrain shown there. You want to have it be able to run a search. Whenever it's faced with a new terrain, you want it to run a search. Find the optimal sequence of footsteps across this new terrain on its own without you doing any fine-tuning for this new terrain, and then get across on its own. Right? So the idea is that this should work for any new terrain somebody presents the robot with that's somewhat reasonable for this size of robot. There's 2 parts of this problem usually. Low-level control. What that means is moving 1 foot from a current location to a new location. So 1 footstep. At the time we started working on this problem, that problem was solved. It's solved by running a search over just a low number of degrees of freedom, and you find an optimal motion of that foot without hitting any obstacles. Let's assume you know how to run this search, then you're left with the problem of where should you place the feet? One argument you could make is you should place the feet in a good spot where the robot will not slip and slide, and so forth. Now, that's actually hard to decide what that means. What do you care about? You care about the slope underneath the feet, because if the slope is very steep, it might slide more easily. You care about whether there are steep drop-offs close to the feet, because if there are, then if you do slide, you might all of a sudden drop a lot. You care about the height differential between different feet, because you don't want the front feet to be really high up and the back feet to be really low. It might not be a good position to be in. And you care about the center of gravity of the robot to be within the support triangle of the 3 feet that are currently placed on these rocks. You might not just care about it being inside the support triangle, but you might care about the margin with which it is inside the support triangle. Want that margin to be high. In total, we came up with 25 things you care about. So now to design a reward function for this task, what you need to do, or could do, is to say, well, I'm going to take a weighted sum of each of these features, and that way for each pose of the robot, I can compute the corresponding reward. Okay, that's great, but now how do you find those weights? That's a lot of weights to choose. You can try to tune them by hand. We tried. It's actually really hard to get those weights in a good position. So we said, well, let's learn those weights. Let's do machine learning to find the reward function. So rather than machine learning to find a policy or a trajectory, machine learning to find the reward function. The reward is of this format. We've done a lot of learning of this format, some weights times features. You get expert demonstrations. That's sequence of states. Okay. You get some initial policy, pi 0. And then you repeat this procedure. You say, well, let's find the set of weights that make the expert, which is your demonstration that you saw, obtain a higher score, W times f of s, than any of the other policies I've considered so far. That's like a perceptron. The other policies are the negative examples. Your expert features is the one positive example, and you learn the classifier that makes the expert the positive class, and all the others the negative class. Okay, so that's your perceptron. Then you solve your Markov decision process for the optimal new policy, the optimal sequence of footsteps. That is your new control policy that might now be the best one. And you put that in your pool of alternative policies that you're willing to consider. And you repeat this process. So why do we have this iterative procedure? The other way to do it is to say the expert policy should be better than all policies. But that's a lot. That's a lot of negative training examples, more than we can enumerate. So what we do is we generate the relevant other policies as we go along. Whenever we have a weight vector, we check for this weight vector, which is the most relevant negative example. Let's pull it in our training data and then repeat this process. Okay, let's take a look at how that works. Here's what happens if you don't do any learning. Meaning, you set all the weights equal to 0. So every pose of the robot is equally good. There's a fertile control. You need to get to the other side. A low-level control trying to do its thing. Putting the feet, or trying to put the feet in desired locations. It tried hard, it got stuck, it got unstuck, but it didn't really make it across in a very good way. Here's what happens after you learn a set of weights. What we did is we demonstrated this is actually a testing terrain, meaning that the terrain you're going to watch the robot walk over is a terrain that didn't exist at the time we were learning the weights. So we built our own, fabricated our own terrains, demonstrated the robot across, found weights, and then a few months later, the funding agency sends us new boards, and we say, let's see how well this works on the new boards, right? That's the idea here. And it is testing in the purest sense of the word, in that we didn't even know what the testing data was going to be at the time we were learning. So the feet still slip and slide, but when they do slip and slide, which is unavoidable, they slip and slide in a very benign way. And this robot, this way, got across the fastest way. This was the state of the art at the time when we were working on this. Okay, what's left for us? Next time, we're going to look at the final contest results. We're going to look at a very subjective view in terms of what's next in robotics. Take it with a grain of salt, but I think it's fun to get a subjective view sometimes. Then we'll look at Pac-Man Beyond the computer game. You'll see what that is. And then we'll see where you can go next at Berkeley in terms of taking classes in artificial intelligence. All right, see you on Thursday.